audible now? Okay.
Sir, sound is
Yes.
repeating.
Now it's gone. The repetition is gone.
Yes, sir. Now gone.
Okay. I hope everyone is able to unmute and talk if you want. So I have modified the settings for everyone. Okay. Those who join late may not be able to talk. So let's start. Hope you can see the screen. So in the previous class, we have discussed the Kirchhoff's voltage law and the Kirchhoff's current law, and we have seen some examples on how to solve some of the network problems using these rules. So we'll continue this with this problem. After doing two numerical, then we'll start with the new topic. So what is the current I1 and I2 for the network shown? Which rule you should use? KVL or KCL?
KCL.
KCL. The Kirchhoff's current rule. How many principal node can you notice here in this figure?
4. A, B, C, D.
Okay. So we are asked what is I1 and what is I2. So what does KCL say? Sigma I at any node is equal to
0.
0. So the incoming currents and the outgoing currents are marked with
Sir,
respect to
I1
this entire node.
equal to minus 6 ampere, I2 equal to 9 ampere.
A1 equal to
Minus
yeah
6.
yes. Okay, so with respect to this node, we can add up all the currents. So let us start with this one. So 3 ampere is leaving, so we can write minus 3 here. 2 ampere is entering, so you can put plus 2. Again 7 ampere is entering, so you can write plus 7. I2 current is flowing out, so you can put minus I2. Similarly, 1 ampere is flowing out, so you can put minus 1. And the last 4 ampere is entering, so you can put plus 4. So this should be equal to 0. That is the algebraic sum of the current entering the network should be equal to the current leaving the network, or the algebraic sum should be equal to 0. So if you add up all these, you can find that this is minus 1 plus 6 plus 5 and plus 4 is equal to
9.
get this is 9 ampere. Okay. So you got I2. Now what about I1? I1 is this current. So what is the current that is coming here at the C node, and what is the current that is going out here? Right.
At C, incoming current 3 ampere.
Yes. So I2 is leaving. So that is 9 ampere minus 9 ampere. And here minus 1 ampere. Then here plus 4 ampere. Okay. So the net current is minus 9, minus 1, minus 10 plus 4 is equal to minus 6, right? Minus 6
Yes,
is
sir.
going to flow like this. So whatever is coming in has to flow out. So the current I1 is equal to minus 6 ampere. Any doubt for anyone on how we solve this? If there is no doubt, we can move to the next problem. Find the current I for the circuit. So I is this current that is flowing out. Again, we have to use which rule? KCL, right? So sigma I is equal to 0. Only thing, the node is shown like this entire thing. Whatever is in this, what do you call, this closed shape is the node we can take. At least it's some network elements are inside that, but don't we don't have to consider that because we are looking at what our currents are entering into the network, because we need to find only what is coming out of the network. So starting from here, plus 2 is entering, here minus 3 is leaving, sorry, minus 3 is entering,
5 ampere.
so plus minus 3, okay. And here 4 ampere is leaving, so it should be minus 4. I is leaving, so it should be minus I is equal to 0. For I is equal to
5.
5 ampere or minus 5 ampere.
So 5 ampere.
Check
No,
this
sir.
Kirchhoff's current law.
Yes, sir.
Don't
Minus.
forget about the sign convention. See, 2 ampere is entering, so you have to write plus 2. Here, minus 3 ampere is entering. So, entering means I have put plus here. Okay. To denote that, it's the current that is entering. And how much is entering? Minus 3 ampere is entering. And here, 4 ampere is leaving. Leaving means you have to put minus sign here. 4 ampere is leaving. And what is I doing here? I is also leaving. So you have to put minus I. So sigma of all the currents should be equal to 0. Now you bring I to the right hand side. So what is remaining is 2 minus 3 minus 4. So that is minus 7 plus 2 is equal to minus 5 ampere.
Minus 5.
Okay. It may seem very simple, but if you don't strictly follow the sign convention, some mistake will happen. So be very careful with the rules. You either stick to one rule, that is, you take that the current entering the node should be taken as positive, the current leaving should be taken as negative. Okay, so that is what the convention we are following all throughout. Some textbooks may present the other way. In those textbooks, they will take current entering the node will be negative and current leaving the network will be taken as positive. If you are following that convention, you have to follow that convention throughout. Don't mix the conventions. There is
Yes,
some
sir.
error will happen. Any doubts?
No, sir.
Anybody got any doubts? I hope it is clear. Find the equivalent resistance for the circuit shown. Equivalent resistance means replace this entire network by a single resistance. That is the meaning of finding the equivalent resistance. How can we replace this entire network with by means of a single resistance?
An ohm.
Yeah, 10 ohm is correct. So how to approach this problem? You can approach this problem by starting here. We see that we have 20 ohm parallel with another 20 ohm. Okay. So what is the net resistance of this entire thing? It will be
10 ohm.
20 parallel 20, which is equal to 10 ohm. So that should be equal to 10 ohm. Now you see these two. We can see that 10 is in series with another 10 ohm. So 10 series with another 10. So that is equal to 20 ohm. So this entire thing is now 20 ohm. Now you see the entire network. So what we see is this 20 ohm parallel with this 20 ohm. Okay. So here we have 20 ohm and here we have 20 ohm. So we have 20 parallel 20, which is equal to 10 ohm. So that's how we can approach these kind of numericals where some resistors are given. Here it was very easy because we can see that the resistors are same. For example, here it is 20, so here it is also 20. So we can take half. If it is not equal, then we have to use the formula that we have drawn before. What was that? R1 parallel R2 is equal to R1 R2 divided by R1 plus R2. If R1 and R2 are not equal, if R1 and R2 are equal, then we can write R1 parallel R2 is nothing but R parallel R, which is equal to R by 2.
By 2.
Okay. Next one, determine the equivalent inductance of the three parallel inductances shown. So inductors are similar analogous to resistors, right? So we can replace them. We can treat them like we treated resistors. So when inductors are in parallel, we can write that 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus
5
1 by L3.
millihenry.
Yeah, 5 millihenry is the correct answer. So 1 by L equivalent is equal to 1 by 10 milli plus 1 by 20 milli plus 1 by 20 milli. So these two will constitute to be. So these two elements you can replace it with 10 millihenry. Now this 10 millihenry parallel with this 10 millihenry. Okay. So the result will be 5 millihenry. Any doubts in that?
No, sir.
Shall we proceed? Okay. Express the total capacitance of the three capacitors in figure as shown. So capacitors in series should be treated like we treated resistors in parallel or inductors in parallel. Whereas capacitors in parallel should be treated like resistors in series.
C2 plus C3 in bracket into C1 upon C1 plus C2 plus C3.
Yeah. So first we can start with this C2 and C3. So we have C2 parallel C3. So that is equal to C2 plus C3. So this is our C2 plus C3, and that is now in series with the C1. Okay, so they are series. So it should be treated like parallel in resistors. So we had to multiply C1 into C2 plus C3 divided by C1 plus C2 plus C3. So this is the total capacitance. Are everyone is following this?
Yes, sir.
Yes, sir.
Okay. Any doubt, you can interrupt and ask me. I will explain once again. So the basics we have covered yesterday. That this is only application of the topics that we have covered yesterday. We have seen how we can treat inductors and capacitors in series and parallel combination. Okay. Moving on. Think about this problem. Somebody is sleeping peacefully. Who is that? Snoring and sleeping. Ashleisha Divedi, are you there?
Yes, sir.
Okay, so this is a typical example in measurements. So when you undergo a course in measurements, you will be able to appreciate this numerical problem. So the paragraph says that the circuit shown in this figure is a voltage divider. Okay, so we have seen what is a voltage divider. So when we have series resistors like this, then we have seen that the total voltage will be divided among these resistors. So we will call this as a voltage divider circuit. Okay. Now another name they have said it is equal. It is called as attenuator also. Then they say that when it is a single resistor with an adjustable tab, then this it is called a potentiometer or port. In short, we call it as a port. So port is nothing but we have a resistor like this. We have a resistor like this, and we have a variable lead like this, which could be moved along this resistor. So we can move this to and fro like this. So as we move this, we will get a variable resistance across the this terminal. So let me label the terminal 1, 2, and 3. So the resistance across 1 and 2 will always be a fixed resistance. So this will be fixed. Okay. R across this will be always fixed. Whereas if we take the voltage or resistance across this 1 and 3 terminal, we can get a variable resistance. So this is variable. And across this also we will get a variable resistance. As we move this lead to and fro, we will get variable resistance in between 1 and 3 and 2 and 3. So this device is called a potentiometer. So we can have voltage divider like this, where we have a fixed resistance like this. The other option is we can have a variable resistor like this. Okay, where we have a tap that is movable. This tap is movable, and we can get voltage divider. So why is it called voltage divider? It's a similar resistor. Now, if I can apply some voltage here, say I give a voltage V across this, then in between 1 and 3, in between 1 and 3, and in between 3 and 2, I will be able to get variable voltages, which will be divided by a particular ratio, which is equivalent to the resistance that is going to come in between 1 and 3 and 2 and 3. So that is the meaning of that. Now coming to our problem. Here Vm is a voltmeter. So what is a voltmeter?
It measures the voltage across two terminals.
Yeah, a device used to measure the voltage is called a voltmeter. So, and what is the internal impedance of an ideal voltmeter? So this entire thing is a voltmeter actually. Okay, so it is composed of two parts. First one is called a galvanometer. The second one
It
is
should be
called a
zero.
resistor. What should be zero? So whatever is shown here is called a galvanometer, and this one is called a resistor. Okay. So what is the purpose of using voltmeter? To measure voltage. Okay. We use voltmeter to measure voltage. Now in this for measuring what is the voltage coming across this 250 ohm resistor, we are going to attach a voltmeter to the circuit and see what is the reading going to come here. Okay. So inside a voltmeter we always have a series resistance connected, which is having a very high impedance. Okay, so R is very high. Okay, so this is as compared to the resistance of the circuit which we are going to measure the voltage. So R is very high as compared to it's 250 ohm. So that is the condition. Otherwise, what will happen is that as soon as we attach this voltmeter, if R is very low, what will happen? Whatever current is coming here, instead of flowing through this path, it will take an alternative route through our voltmeter. So that thing should not happen. So how to prevent this? So this should not happen. So in order to prevent that, we should put R to be very high, so that the current through the circuit will not enter our voltmeter and cause any loading effect. This effect is called a loading effect. If loading is going to happen, what happens is that, so we use a voltage divider circuit to divide the V in voltage in a particular ratio. If you connect a low resistance voltmeter like this, then all the current will come and flow through this voltmeter, so that the current will not flow through this resistor. Now what happens to this voltage? This voltage will now gets disturbed. It will become lower. It will decrease. That effect is called loading effect. Understood? So that is the relevance of this circuit. So it comes in the case of measurements. Now we are given this question. So for circuit, we don't have to know all these things. So these are the preliminaries that you should have knowledge of. So when we come to circuit, you can simply replace this. So this is our voltage divider circuit. To which we are going to apply the voltage V in. And here we have the voltmeter. So we are not interested in the galvanometer. So assume that the galvanometer impedance or resistance is equal to 0. So we have the only the voltmeter resistance coming here. And here we have 2250 ohm, and this is 250 ohm. And we are asked what is this V out. So this V out is going to be measured by our voltmeter. Okay. So case 1, so we have to find what is V out for 3 different cases. So in case 1, R is equal to
Infinity.
infinity. Case 2, R is equal to 1 mega ohm. And in third case, R is equal to 10 kilo ohm. And the fourth case, R is equal to 1 kilo ohm. So these values, when you substitute, you will understand what is going to happen. So what we have to find out? We have to find out the ratio V out to V in. Okay. So which result we can use? Yesterday we have written the equation for voltage divider. So I will elaborate this method. Actually, this ratio I have not completed. So I will write the ratio with respect to, let us say, 2 resistors or 3 resistors in series. So if I have R1, R2 and R3 in series, then let V1, V2 and V3 be the voltages that is going to come across these resistors. And let V be the total voltage that is applied. So we can write the equation like V1 is to V2 is to V3 is to V is equal to R1 is to R2 is to R3 is to R1 plus R2 plus R3. So that is how the voltage is going to get divided across these resistors. Okay. Now use that result here so that we can easily find out what is the voltage coming here. So we can write V out is to V in is equal to R is to this plus this entire thing. Okay. So 2250 plus 250 parallel R. we are asked what is V out is to V in. V out by V in is being asked. So that is nothing but R upon 2250 plus 250 parallel R. So first case is when R is equal to infinity. So what happens when R goes to infinity?
Ratio will be higher.
Yeah. So here is the this we can call as the equivalent resistance. So whatever is shown in the red, I can call is as the equivalent resistance, R equivalent. So R eq is nothing but 250 parallel 250 parallel R. So that is equal to this thing what you have written here. Okay, 250 into R divided by 250 plus R. So when we have R is equal to infinity, we are connecting an infinite resistance in parallel with a low resistance. So what will happen to this? Yesterday also I told, when we have more than one elements in parallel, then the net resistance will be lower than that of the lowest smallest one. So 250 is very much small as compared to infinity, so the gap is too high. So what will happen is when we put those resistance in parallel, so the equivalent resistance R, as R tends to infinity, then R equivalent will tend to 250, right? So you can take the limits here. So you can make a limit R tends to infinity of 250 into R divided by 250 plus R, right? So this is nothing but 1 upon R, right? So when this R tends to infinity, then this quantity will tend to 0, so that the value will be equal to 250 ohm. Okay. Hope you understand.
Yes, sir.
Yes, sir.
So when that is going to happen, so here what I've done is that this should be equal to R equivalent. Okay, it should be equal to R equivalent is to this entire thing where R equivalent is 250 parallel R. So this is our R equivalent.
1/10.
Yeah, that will be equal to 1 by 10. So here it should be equal to R equivalent. It's R equivalent. Okay. Now what happens to our V out upon Vn, it will be equal to 250 upon 2250. So that will be equal to plus 250. Okay. So that should be equal to 250 divided by 2500. So that will be equal to 0.1. Okay. Now coming to case 2, what is happening when R is equal to 1 mega ohm? R is equal to 1 mega ohm. What will happen? We'll have R equivalent is equal to 250 parallel 1 mega. That is equal to 250 into 1 into 10 power 6 divided by 250 plus 1 into 10 power 6. Okay. So that we have V out by V in is equal to here also you can make that approximation. So this is the equation that we are going to use here. So R equivalent upon 2250 plus R equivalent. So this is our R equivalent. So what is this? This is 1 mega ohm, whereas 250 ohm is very small as compared to 1 mega ohm, right? So we
Yes.
can neglect this 250. We can neglect this 250. So we can write this as equal to
250.
250 ohm itself. So approximately this is equal to 250 ohm. So we have 250 upon 2250 plus 250, which is again equal to 0.1.
0.1.
See, so the ideal voltmeter should have the series impedance equal to infinity. That is an ideal case. But practically infinite impedance is not possible. So we have to make it as big as possible. So 1 mega ohm is a very large value. Now we will take up the next case when R is equal to 10 kilo ohm. Now we are slowly approaching the near to 250, right? We are slowly approaching 250 ohm. So that is 40 times 250. So what will happen to our ratio V out is to V in? Now R equivalent becomes 250 upon 2250 plus 10k, 10 into 10 power 3.
244.
Yeah, 243.9. So while substituting this, it will be 250 upon 2250 plus sorry, 243.9 upon 2250 plus 243.9. So that ratio will come to point. This ratio will start to reduce. It will start to decrease.
0.09.
0.098. Now what happens when the voltmeter resistance is too small? That is very much comparable to the impedance 250, making it to 1 kilo ohm. R is equal to 1 kilo ohm. Then V out by V in. We can see that it is still dropping. So we can do this as exercise. It will drop to 0.082. Okay. So our measurement will create errors when we have the voltmeter resistance dropping. Okay. So ideally we should have the voltmeter resistance should be infinity, so that our measurement will not be disturbed. So why do we use a potential divider? We use a potential divider to divide this input voltage in a particular ratio. So we should be able to get that constant voltage across this. So there should not be any loading effect as we add any circuit towards the right side, or we use any measuring instruments to measure the voltage. That should not happen. So you should have some consideration on what is the impedance that is coming here. So ideally the measuring instrument should have very high impedance as compared to the impedance here, or for DC it is resistance. So the measuring instrument should have very high resistance as compared to the resistance that we are going to measure.
Sir, how it act
Okay.
as an
So
attenuator?
we'll yes.
Sir, how voltage divider act as attenuator?
How voltage divider will act as?
Attenuator. In the question it is written.
It is also called attenuator because this is not a very recommended method of dividing the voltage. Why? Because it could be used for small circuits like small power circuits. How it is going to work is that when the current is going to flow through these resistors, power dissipation is going to happen. So we are passing some current here. So it will cause some I square R loss in here, as well as some I square R loss here. So we are attenuating some of the voltage. We are dropping some of the voltage here, and we are taking out the remaining voltage here, to which we are connecting the various instruments. Understood. So this is not a very recommended method of voltage division because it is attenuating, dissipating power and taking out whatever is coming remaining to use for our circuit.
Okay, sir.
Attenuator means attenuation of power is happening. That is the meaning of attenuator. So any circuit that is used to attenuate power is called an attenuator. So while we were discussing resistors, we said in order to dissipate power, there should be a resistor. Inductor and capacitor cannot attenuate power. Okay. Find all the branch currents in the network shown. So how will you start this problem? Where to start?
With node A.
How many sources are there?
1.
How many sources are there? One source is there. Is it a current source or a voltage source?
Current source.
It's a current source. Is it a dependent current source or independent current source?
Independent.
It is an independent current source because we see the symbol here. It's a circle and we see the direction of the current also. So how should I mark the current? In the upward direction. How much current is flowing in the upward direction? It is given by this value. Yeah, 13.7 ampere is going to flow in the upward direction. So that is where we can start. So here a node is marked. A principal node is marked as A, and to that node 13.7 ampere is going to come inside, and it is going, I3 is going towards the left and I4 is going towards the right. So how can we modify the circuit and represent in a simple manner? Here we are having two resistors in parallel, and on the left hand side we have 5 ohm in series with parallel combination of 12 ohm and 8 ohm. So by redrawing this circuit, we can draw a similar network like this. And here we have the node A, 2 ohm is here, 13.7 ampere. So what about the value of this resistor?
2 ohm.
Yeah, it will be 6 parallel 3, which is 3 into 6, 18 divided by 3 plus 6 is equal to 9. So that is equal to 2 ohm. What about here? That is 5 series with parallel combination of 12 and 8. So 12 parallel 8 is 12 into 8 divided by 12
9.8.
plus 8.
4.8.
Are you telling the final answer?
Yes, sir.
9.8 is the final answer.
No, okay, you are telling the resistance. So this is equal to 9.8 ohm, right? Now 13.7 ampere is coming here. Okay, incoming, and it is getting split up. Let me call this as I1 and this is I2. So what should be the values of I1 and I2? Which rule should we use?
Current divider.
Current divider rule. Okay, you can use that rule. So current divider rule also we can use that equation. So I1 is to I2 is to I. Let me call this as I, which is equal to 13.7 ampere. That should be equal to 1 by R1 is to 1 by R2 is to 1 by R1 plus 1 by R2. So this we have to call as R1. This we can call as R2. So what is I1? I1 by I could be written as 1 by R1 divided by 1 by R1 plus 1 by R2. So if the values are given, then it is very easy. Otherwise, don't take the pain of doing all this ratio thing and all. It is better to directly use our current divider equation. Hope you will remember. So I1 is nothing but the total current into the opposite branch impedance. So opposite branch is this one. So I1 is flowing here. So the opposite branch is this one. So it should be 2 divided by sum total of all the impedances. So that should be 9.8 plus 2. This is I.
2.32 ampere.
Yeah, I is equal to 13.7 ampere. So this will yield 2.32 ampere. Okay. And I2 will be equal to 13.7 into the opposite branch resistance. So for I2, the opposite branch is 9.8. So that will be 9.8 divided by 9.8 plus 2.
Eleven point 37.
Yeah, it will be 11.38 ampere. Okay, approximate it. So we have the currents that are now flowing through these branches. We can mark in the original circuit what are the currents. So here what is coming is 2.32 ampere is flowing towards the left, and towards the right, is flowing 11.38. Okay. So what about the currents I1 and I2 here? Again, you
I1
use the current divider rule. Yeah.
0.928
Okay.
and I2
So
1.
here you can. Okay. So this is actually we'll write this as I3 to avoid the confusion. So towards the left is flowing I3 and towards the right is flowing is I4. Okay. There's some confusion might arise. So again, use the current divider rule here to find I1. The incoming current is 2.32 into the opposite branch impedance. So this is I1. The opposite branch is this one. So impedance here is 8 ohm divided by 12 plus 8. So that will come to be, how much it was coming?
0.928.
Okay, 0.9. Okay, 93. Okay, and here. Similarly, I2 is equal to 2.32. Okay, you can directly subtract also, since already know that incoming is 2.3 is coming. I2 is equal to 2.32 minus 0.938. So that will be equal to 1.39 ampere.
Yes, sir.
So incoming is this, and here what is flowing is 0.93. So what should flow here by using KCL? This current should be automatically equal to 2.32 minus 0.938. This is 1.39. What about on the right hand side? 11.38 is coming in, and I5 and I6 is flowing out. So we'll write here I5 is equal to 11.38 into opposite branch impedance 3 divided by 6 plus 3. Similarly, I6 could be written as equal to 11.38 minus I5. So that will be 3.79.
Yes, sir. 3.79.
We should get 3.79 ampere. So this is 11.38 minus 3.79. So that will come to
7.58.
yeah 7.59. So I hope that that is clear to everyone. Any doubts? Just we have to reduce the network as required to make a simplified circuit, so that we can know what is the current that is going to the respective branches. Then again use the current divider rule repeatedly until we can find all the currents. So in exams and all, we may be asked only, for example, we may be asked only to find I6. So in that case, we don't have to do the other steps. Only find out what is the current that is coming towards the right, then use again current divider rule in order to find I6. If it is like an objective type question, if you are asked to find all the currents, then you have to follow all these steps to find out what are the currents across all branches. Okay. So take care that this 5 ohm, here it is series, it is present there, but here you don't have any resistance. So it is most likely to be omitted. Don't omit it. Consider it as a series, and this should be the parallel combination to solve the network problems. So with that, we will conclude this chapter. If anybody has gotten it out, we can ask.
No, sir.
Clear, sir.
Okay, okay, we will continue. So in this chapter, we will be seeing some basic analysis methods. Some of the analysis methods are the branch current method. Then we have the mesh current method. Then we have some method called as the matrix method. Then we have the node voltage analysis methods. So these are like how we can approach a network problem and how we can solve this. For example, in the branch current method, these are certain algorithms on how we can solve these network problems. So in branch current method, first thing we have to do is a current is assigned to each branch in an active network. So for each branch, we will assume a current, like we saw in the previous problem. And then we will be using the Kirchhoff's current law at the principal nodes and the voltages between the nodes employed to relate the current. Okay, then we will get series of simultaneous equations which can be solved. So I will demonstrate one example in order to understand this method. So the question is to obtain the current in each branch of the network. And we are asked to use the branch current method. Okay. So if in exams the method is specified, then you have to use that particular method to solve the numerical problem. Otherwise, also you can solve the numerical problem. For example, you can use mesh current equation and write the KVL and solve this equation, this question. Okay. But when if it is asked specifically that you have to use the branch current method, then you have to follow the algorithm that we have just read. So first thing is a current is assigned to each branch in an active element. So we can see that there are how many branches? 3 branches, right? One branch is like this. So we can assume one current is coming here. That is labeled as I1. Then another current is leaving here. That is written as I2. And the third branch, which is carrying current I3. Okay. So in the branch current method, the current is assigned to each branch in an active element. That we have done. The next step is Kirchhoff's current law is applied at the principal nodes and the voltages between the nodes employed to relate the currents. So next step is identify which all are the principal nodes. So here we have a node, but we will not consider that. That is a symbol node. Here also we are having a symbol node. So we have to identify only the principal nodes. For example, A and B are the principal nodes because it is connecting 3 or more branches. So in A also we have 3 branches coming in, and B also we are having 3 branches coming in. So A and B are the principal nodes. Then with respect to that, we have to write the Kirchhoff's current rules. So what does the KCL say?
Summation of zero
And I is equal
at
to 0.
is zero.
Equal to 0. Or incoming current is
Is
equal to
equal
the outgoing current.
Outgoing current.
So here I1 is the incoming current, right? So I1 is equal to I2 plus I3. So that will be our first equation. Then we can write a series of equation. For example, let us call this voltage, that is the voltage coming across the AB terminal, that is this branch, as equal to VAB. I don't have space to write. So let me call this as VAB, this voltage. And I3 is flowing. Okay, now with respect to VAB, so you can mute your mouth. Sorry, mic. So with respect to VAB, we can write. So I1 is coming in. So what is VAB? So this is this voltage VAB, right? So we have 20 volt here, and some voltage is getting dropped across this 5 ohm resistor. So the voltage that is dropped across 5 ohm resistor is 5 into I1. Okay. So we can write just like the Kirchhoff's voltage rule, we can write VAB is equal to 20 minus. Why is it minus? Because the polarity is marked like this. So current is entering like this. So on the left hand side we have plus and we have minus. So it is 20 minus 5 times I1. Okay. Similarly, we can write one more equation here for the second branch. Here, okay, for the second branch. So it says that VAB is equal to so what it will be. So this is VAB, right? So this is the voltage that should come here. So instead of marking VAB, let me draw like this so that the polarity will also be understood. So this is VAB. So this is VAB, and that is balanced by this voltage. Okay. So how can I write? VAB is equal to 8 plus
2i.
yeah, twice I1. Sorry, twice I2. One more equation you can write for I3. You can write VAB is equal to this voltage. What is this voltage? This resistance into this current. Okay. So VAB is equal to 10 times I3. So we got a series of simultaneous equations. We can eliminate this VAB. How can we eliminate this VAB? Equate any one of these equations. So I will equate these two equations and I can equate these two equations. So I can eliminate VAB and eliminate one variable. So while I do this step, so what minus 5i1. So I will get one more equation 2. And while I do this step, what will be 10 times I3 will be equal to 8 plus 2i2. That is my third equation. Now, can I solve these equations? Are
Yes,
these
sir.
equations solvable? Yes, we can solve because we have three unknowns and we have three equations. So we can get a unique solution for these simultaneous equations. So this is the method called the branch current method. So can you solve and find out what is the values of I1, I2 and I3?
Yes, sir.
So how do you approach these numerical problems? You eliminate one variable at a time. You can either take the third equation. From 3 we can say that I3 is equal to 8 plus 2I2 divided by 10. Then substitute this in. So this I can write as 4 and substitute 4 in 1. So I can write I1 plus, sorry, I1 is equal to I2 plus I3 will be replaced by this result 8 plus 2I2 divided by 10. Similarly, apply 4 in 2 so that we will get 10 times 20 minus 5I1.
I1 equals to 2 ampere, I2 equals to I3 equals to 1 ampere.
Yes, sir.
I1 equals to ampere, I2 equal to I3 is equal to 1 ampere. That's the correct answer. Okay. Now you, those who are not following, so after substituting this, you will get this equation in I1 and I2. If you examine this equation, you will get, you can see that it is an equation in I1 and I2 alone. Similarly, it's a case of this equation. This is also in I1 and I2. So we get two simultaneous equations in I1 and I2. Then you do the algorithm, mathematical algorithm to eliminate one of these by multiplying with a constant and subtracting. Then you will get one value. Let us say I1 you are getting. Then substitute in one of the equations so that you will get I2. Then in order to find I3, substitute the result of I1 and I2 in the fourth equation. So with that you will get I3. So that is the method algorithm you have to follow. So as you said, the final answer you should be able to get I1 is equal to 2 ampere and I2 equals I3 which is equal to 1 ampere. See that you are getting this result after following this method. Now moving on to the next method, which is called the mesh current method. So this method we will be using very often. So whenever we see mesh, it is better. We are normally inclined to use the mesh current method. So in the question, you specifically see that they are asking the um, branch current method only. Then you go for this method because for me personally, I feel that this is a very difficult thing. I don't know about you. If you find it convenient, then you can use this naturally. But whenever I see meshes, I like to prefer to go for the mesh current equation instead of writing the branch current method. So in mesh current method, a current is assigned to each window of the network such that the currents complete a closed loop. Okay. So here we will be writing the loop currents. Okay, we assign a current to each loop. So that's the method. They are also sometimes referred to as the loop currents. Then each element and branch therefore will have an independent current that we will be writing in terms of these loop currents. Then when a branch has two of the mesh currents, then the actual current is given by their algebraic sum. Sometimes we write, for example, we have one mesh like this, another mesh like this, and I like write one loop current, say I1 like this. Another current I will take I2 like this. So in this vertical, the middle part, I will have common of I1 and I2. So when such cases are coming, what is the current flowing through this branch? I have to take this as equal to the algebraic sum of these currents. So I have to take either I1 minus I2 like this. So I am traversing like this means I have to take it as I1 minus I2. Okay. So in this direction, I1 is flowing, and opposite to that, I2 is flowing. When I traverse in this manner, then I have to take this as equal to I2 minus I1, like that. So take the algebraic sum when a branch has two of the mesh currents. Okay. Then the assigned mesh currents may have either clockwise or counterclockwise direction. So here I have shown both in the clockwise direction. It doesn't mean that I have to always take it in the clockwise direction. You can take in clockwise and another in counterclockwise. Only thing you have to assign the signs correctly, or you can take both in the counterclockwise direction. It's your choice. So while discussing, I will be naturally inclined to take in the clockwise direction, which you can follow. Then once the currents are assigned, then we apply the Kirchhoff's voltage law. So we will be having some elements here. So maybe some passive element is here. There will be some active element here, and another passive element will be here. Okay. So current source or voltage source. Then we write the Kirchhoff's voltage law for each of these loop. Okay, if you are having passive element. So we will see with an example so that you will understand better. So we have the same circuit, and we are asked to obtain the current in each branch. We are asked to obtain the current in each branch, and we are asked explicitly to use the mesh current method. Okay. So if the question it is mentioned that you have to use mesh current method, then you have to use the mesh current method. Don't use the node voltage analysis. That may seem similar for this network. Whereas in competitive exam, you can go for the node voltage because you see that the network is very simple and you can find the currents very easily with node voltage. You can directly go for that. But in university exams and all, if the method is mentioned like this, you have to use mesh current method. Similar other descriptive exams also will be asked to use the mesh current method. Maybe in IES exam like that, then you have to use that method only. So what should we do first? First step is we have to assign currents through for each of these meshes. So it's already drawn here. I1 is marked here and I2 is also marked here, and both of those are marked in the clockwise direction. What is the second step? I have to apply Kirchhoff's voltage law. Okay. So I can apply KVL for the first loop. So starting from here, I have 20 minus, here voltage drop is going to happen, right? 5 I1 minus, why it is minus? Because it's again a passive element and I am traversing in this manner. Okay. So minus, in the direction of I1, I have to take plus I1. Okay, and it is opposed by this I2. So in this branch we have got two currents. What are the current? One current is this I1 and the other current is I2 like this. Can you see it correctly?
Yes, sir.
Yes, sir.
Here I1 is flowing down because here we are traversing in the clockwise manner. So it is going down. And what is coming up? I2 is
I2.
going to flow up. So we have to, while we are traversing like this, while we are traversing in the downward manner, then it I1 is favoring us. So we have to take it as plus. Whereas I2 is opposite to our direction of traversal. So we will take it as minus. Okay. So that should be equal to 0. Have we completed the loop? We have covered the entire loop. So after that, we will reach the where we have started. So
Sir,
KVL says that sigma of the voltages is equal to 0.
sir, I1 minus I2
Okay.
into 10.
Yes,
Okay.
sir.
Into 10. Okay. I forgot that. Is equal to 0. Now you can rearrange this and express in terms of I1 and I2 so that you will get one simultaneous equation. Okay. That you can label as first equation. Similarly, so this is for loop 1. Similarly, we can write another KVL for the loop 2. Where you want to start? You can start here if you want. So what should I write? Minus of 2 times I2, right? Because current I2 is, we are traversing in this manner. Okay, so I2 is now flowing this. So I2 is flowing like this, and here I1 is flowing like this. Okay, so I2 is entering this at the plus terminal, so I had to put minus here because we are traversing from plus to minus across this resistor, or voltage drop is happening. So I have to put minus I2. Okay, minus is disappearing. Okay, minus 2I2. What about here? Again, I am traversing this voltage source from plus to minus. So here you can see plus is marked on the top and minus is on the bottom. Inside the symbol you can see, right? Only thing I have written it outside to see clearly. So should I take plus 8 or minus 8?
Minus 8.
Okay, minus 8. Minus. Why minus? Now we are traversing in this manner. Okay. From bottom to top. So I will have polarity mark like this. So I have to put minus 10 into what comes inside the bracket? I2. Now I am traveling in the direction of the I2. So I2 has become positive, whereas I1 is in the opposite direction. So I2 minus I1 into
10.
10 is equal to 0. So you can rearrange this and express it as two simultaneous equations in I1 and I2.
Minus 10 I2 equal to 20.
Equal to 20. Okay. First equation.
10 I1
Yeah, 10 I1
minus 12 I2 equal to 8.
minus 12 I2 is equal to 8. We can easily solve these simultaneous equations and find I1 and I2.
We get same answer. I1 equal to 2 ampere.
Okay, on simplification, you will get I1 is equal to 2 ampere.
Yes, sir.
Sir, I1 2 and I2 1 ampere.
Yeah, I2 is equal to 1 ampere. Okay, so remember that we have to find the current in all the branches. Okay, so we can write the current. This is equal to 2 ampere and this is equal to 1 ampere. Okay, sometimes you may get while solving the simultaneous equation, you will get minus sign here. So suppose this was equal to -1, then how will you mark the current? It means that the loop that you have taken in the clockwise direction is not correct. It should be in the anti-clockwise direction. If you get such an answer with a negative sign, then mark I1 like this, okay, and mark it as 1 ampere like this. But since we are having +1 as the value of I2, you can mark it like this. So I2 is equal to 1 ampere. What about the current here? I2 is entering at this node
1 ampere.
and I1 is leaving. Okay, so this current should be equal to 1 ampere and in the downward direction. So you can mark it as I3 if you want, because the question is asked to obtain the current in each branch. So we have 3 branches. So write the final answer. I3 is equal to 1 ampere. Hope that is clear on how to use the mesh current method. So it is nothing but the application of the Kirchhoff's voltage rule. I'm going on to the this matrices and determinants. I will explain. First of all, we'll write the mesh equations for this network. For example, we are having 3 loops. I1, I2, and I3 are the currents in these 3 meshes or the 3 loops. So I can write first equation as VA minus I1 RA. Okay, so while going here, I have VA minus 2 plus minus IA RA, and coming here, I will have minus I1 minus I2 into RB is equal to 0. So that is my first equation. So on rearranging and simplification, I can write this as equal to RA. So I1 here and I1 here. So RA plus RB into I1. When bringing I2 to the other side, it will become minus RB into I2 plus 0 into I3 is equal to 0. So that is one equation. Okay. Now writing KVL for the second loop, I can start here. So I will start. Minus RB into I2 minus I1 minus RC into I2 minus RD into I2 minus I3 is equal to 0. Understood this equation? So I started off from here. I2 is flowing upward and I1 is flowing downward. So I wrote I2 minus I1. Since it's a passive element, I wrote minus. And here again minus passive element. So minus RC into I2. In this branch, I2 alone is flowing. Okay. Then in the downward direction, I have I2 minus I3 flowing in this direction. And the resistor is RD. So minus RD into I2 minus I3. Now rearrange this equation so that I can write of this form. Some resistor into current, some resistor into I2 current, some resistance into I3 current, like that. So for I1, I have 1. So I have, and bringing to the other end also. So here minus RB into plus I1 will be equal to plus. I bring to the other side, so that I will have minus RB into I1. And for I2, I have minus RB so that becomes plus, and minus RC plus RC, and here I have minus RD, so plus RD into I2. What about I3? I3 I have plus RD into I3. So bringing to the other side, it will become minus RD into I3. Is equal to 0. Are you following what I am doing?
Yes, sir.
Just simplifying it and bringing it to a form like this. Okay. So this is first equation. This is second equation. And I will use a different color for third equation. So the third equation I can start from here itself. So minus RD into I3 minus I2 minus RE into I3, and we are traversing this voltage source from plus to minus, so it should be minus VP is equal to 0. Here I made one mistake. There is one VA here. I skipped that VA. Nobody informed me. So this should be equal to VA on the right hand side. Okay. Here VB is also there. Okay. So how can I write in that form? Here there is nothing for I1. So I put 0 times 0 I1. For I2, I have plus RD. Okay. So plus RD into I2. What about I3? RD and RE. So minus RD plus RE into I3, which is equal to
VB.
VB. Okay, let me rearrange this as and write it as minus VB. So I'll have plus here and I will have minus here. Okay. I'll tell you why I have written like this. So that is my third equation. So why I am writing like this is that I can now represent these three equations in a matrix form, because we are discussing the matrix and matrix method, matrices and determinants method of solving these networks. So how can I write these equations? So how can I write all these three equations in a matrix form? First of all, so we know that I can write this in the form R into I, matrix R into matrix I is equal to the V matrix. How can I write the R matrix? R matrix are these resistances. So along the diagonal, I have RA plus RB. And the second one is RB plus RC plus RD. And the third element is RD plus RE. So what are the other elements? I have minus RB
Sir,
and 0. Yes? Any doubt?
uh, second element it's RB plus RC plus RD.
How we can eliminate?
The second
Yeah, yeah. I made some mistake there, right?
in the second equation, the coefficient of I2 is RB plus RC plus RD. So in the matrix, it's written RB plus RC plus RC.
Okay. Okay. Can you tell once again what mistake I did here? So here, actually, that figure is not coming properly.
In the 2-2 position of the matrix.
Okay.
It's
So in this loop, I have written minus RB into I2 minus I1 minus RC
sir,
into
equation
I2.
is right. Just in the matrix, you have to write RD instead of RC.
This one. This one you're talking about.
Uh,
Are you talking about this one? This underlined one?
no, sir, 2-2 position.
This one. RB plus RC plus. Okay, okay.
RD.
It should be RD. Okay. Okay. Also, coming to the second row from the second equation, what should come here? It should be minus RB. Right, minus RB. Then what comes here is minus RD. This is minus RD. And the third row we have 0. Then we have minus RD and RD plus RE. Okay. And how we can write the current matrix? Current matrix is nothing but all the loop currents. So I1, I2 and I3 we can write as a column vector that is equal to the voltage. So while writing the voltage, I told why we have to how we should write. So when we take the mesh currents like this, and if you're traversing the voltage from minus to plus, then you take that voltage as plus. For example, in VA, we take the mesh one. In mesh current one, it is traversing. We are traversing from minus to plus. So VA should be taken as plus in the matrix. Whereas in the second mesh, loop 2, we cannot find any voltage source there. So there is no voltage, so we have to put 0 there. Whereas in the third loop, we are traversing the VB source from plus to minus when you are moving in the clockwise manner. So that VB we have to put it as minus VB. So this is the matrix method of representing our mesh voltage equations. So what I have done is I have drawn the mesh currents for all the three meshes. I1, I2, and I3 are the mesh currents or loop currents. Then I have written the Kirchhoff's voltage rule. I have applied the Kirchhoff's voltage rule to write all the uh, voltage drops and equated to equal to 0. Then from there I have picked up the coefficients of I1, I2, and I3, and I have created the matrix which is called the resistance matrix. Okay. Then I have picked up all the loop currents and I have written the current matrix, and I have picked up all the voltage sources and I have written the voltage matrix. Now, how we can easily write this? Anybody got any idea how we can easily write this matrix without writing all the KVL and KCL? If you have read the textbook, you will know. In the textbook, it is mentioned how we can directly write the
Yes, sir.
how we can write it directly.
So consider
How to how to write the R matrix? The current matrix and voltage matrix I have already told you.
Yes, sir.
So current matrix is the easiest one. You can simply write I1, I2, and I3. So I1 and I2 and I3 are the loop currents. So I can simply write the current matrix like this: I1, I2, and I3. Now to write meshes. So if you are traversing the voltage VA from minus to plus, then take it as plus VA. So the first element is the are the sum of all the voltage sources that are coming in the first mesh. Since in the first mesh we are having only one voltage source and we are traversing from minus to plus, then we will write it as directly equal to VA. If in case there was one more voltage source like this with polarity minus and plus, then what should be that element? Let this be equal to say VC.
Minus VC.
Not minus VC. I am asking if VA and VC are both there. So how should I write?
VA
I
minus
should write VA minus VC. Right. Okay. If instead of VA was absent and only VC was there, then it will be equal to minus VC. Okay.
Yes, sir.
So that's how we write the voltage matrix. The second element is the voltage sources that are coming in the second loop. So in the second loop, there are no voltage sources. So I have to put 0 there. Similarly, the third element of the voltage matrix is all the voltage sources that are coming in the third loop. So while we are traversing like this, the third loop, we can see only one voltage source, that is VB. And since we are traversing from plus to minus, so that should be put as minus VB. Now coming to the resistance matrix. So the first element of the R matrix, the resistance matrix is all the resistors that are coming. Sorry, actually I am first writing the diagonal elements. So the first diagonal element will be the sum total of all the resistors that are coming in the first loop. So while I traverse like this, I can see only two resistors. First one is RA and the other one is RB. So I have to take the sum total of RA and RB. So that is the first diagonal element. Second diagonal element, we have to go to the second loop and see what are the resistors there. So here I can see that while traversing this loop, I see how many resistors? RB, RC, and RD. So I can write RB plus RC plus RD. And the third diagonal element is for the third loop. So if I traverse here, I can see there are two resistors. So I have to take the sum total of this. So that is RD plus RE. So the diagonal elements are the easiest to write. So I have written all the diagonal elements first. Now coming to the off diagonal elements. So this element. So let me call this as R11. So generally we can call the resistance matrix like R11, R22, R33 are the diagonal elements, and this is R12, this R13, this R21, R32 and R23, R31, R32 and R33. Okay. So what is the R12 diagonal element? This element.
minus RB.
So that is the element that is common to loop 1 and loop 2. The branch element that is common to loop 1 and loop 2, and that is RB alone. Okay. Now how to attach a sign to this? The sign is considered such that if in loop 1 and loop 2 we have drawn two currents, one is I1 like this and another is I2 like this. So one current is going downwards, the other current is going upward. So if the loop currents are in opposite directions, then put that is as minus sign. Understood? Since we have taken the loop currents in mesh 1 and mesh 2 as clockwise direction, we can see that in RB, the currents are flowing in opposite direction. So you have to put minus RB. That is the rule. And the R13 element is the resistance that are, or the elements, passive elements that are common to loop 1 and loop 3. So if you check, loop 1 is here and loop 3 is here. So there are no common elements shared by loop 1 and loop 3. So that should be equal to 0. Now coming to R21 element. So R21 is the element that is common to loop 2 and loop 1, which is nothing but the same as this RB itself. So I can put this as RB. Why minus? Why minus? Because the currents, loop currents are in opposite direction. One is going downwards, I1 is going downwards, I2 is going upward. So I put minus sign here. Then the element R23 is common to loop 2 and loop 3. Here also the currents are, and that element is RD, nothing but RD, and the currents are in opposite direction. So I have to put minus RD. Okay. Similarly, you can fill the remaining elements. Also, once you write the upper matrix, then you can transpose it and write the lower diagonal elements, because this matrix is symmetric. Okay, you can transpose it. I mean, the transpose of this matrix is the same matrix itself. Okay, so once you are able to fill RB here and 0 here and minus RD here, then you can write minus RB here and RD here and 0 here. So that is how we can easily write this matrix. Okay. So one question I want to put across to you. You have studied matrix method from maybe in your +2, right? You know, addition of matrix, subtraction of matrix, multiplication of matrix, division of matrix, etc. Right? Am I right?
Yes, sir.
Yes.
Yes. So while you studied, you have seen that you can solve a lot of solution of simultaneous linear equations, and all those purposes you can use the matrix. For example, this matrix also you can solve. Why we wrote this as a matrix? We can solve this matrix. How we can solve? For example, what is asked is, we are asked to find what is the current matrix. We are asked what is I1, I2, and I3. So I1 and I2 and I3 is nothing but I1, I2. Okay, let me write it very briefly. What is this I2? I2 matrix is nothing but R inverse, R matrix inverse into the V matrix, right? So which method do you know to find the inverse of the matrix? It is a rule called Cramer's rule, right? So instead of solving the simultaneous equation, you can invert this matrix. Once you are able to write the matrix like this, then you can use the R inverse and you can multiply it by V. This you can do in a calculator also. If you are using a scientific calculator, you can just write this matrix and verify whether your answer is correct or not. And multiply this V. That is, we use the adjoint A by determinant A to find out what is
Inverse
R
of the
inverse. Okay, adjoint R divided by determinant of R. Okay. So you can solve the network equation. So you know that matrices are used to solve simultaneous equation plus other things also. So have you wondered why you are doing the matrix? That is my question. Many times you see that we represent equations in matrix method. So why are we representing in matrix method? Why don't we solve in this simultaneous method? Anybody has wondered this? Put this question. Sir, why should we write in matrix? I know how to solve in simultaneous method. Then why should I write matrix method? Any answer for that? Any guess? Wild guesses? If you give an answer, then we will proceed to the next one.
So
So why are we using matrix method?
it's easier to solve in matrix when we have more than two variables.
Is it easier? So what if we are having four loops like this? Then it will become a 4 by 4 matrix. If you are having 5 loops, then it will become 5 by 5 matrix. Then how will you find the determinant of like this? We have to do the adjoint A for all these elements, right? It is very difficult for us. For a 2 by 2 matrix, which is very easy. 3 by 3 also we can do. Okay, somewhat humanly possible. Then it comes to 4 by 4 matrix, it becomes more difficult. So in that reply itself, the answer is there. Humanly, it is impossible to do larger matrix. But who can do solve bigger matrices? Something not possible by humans can be done by
Calculators.
computer. Okay, calculator is a computer. Okay. So in computers, if you want to write a program so that we give the values of the branch elements, and we want to find out the branch currents, and you want to write a program for that, then you cannot write an algorithm for this, how to solve the simultaneous equation the way we are doing by elimination of the variables like that. The computer, it is not possible. It is very difficult to write algorithms for this. Okay. Whereas it is very easy to write algorithms to find this one, how to find the determinant of a, how to find the adjoint of a matrix, then how to divide the matrix to find the R inverse. Also, we can write algorithms to multiply two matrices. Understood? So remember that this matrix method is for you to understand that it is the method used in computers to solve the problems of the network. So if you want to write a program, then you have to write the program using this matrix method. So that is the answer to the question that you had never wondered why we are studying matrices. Okay. Now moving on, one more topic we will cover today, that is called the node voltage method. Okay. So the node voltage method, in node voltage method, one of the principal nodes is selected as the reference node. Okay, then equations based on Kirchhoff's current law are written at the principal nodes. So, for example, in this figure, uh, principal nodes are node 1, node 2, and node 3. So you can select any one of these nodes as the reference node. So since 3 is having all the more number of branches coming in, let us select 3 as the reference node. Now we have done the first part. First part is to identify a reference node. So we have multiple principal nodes, and out of that we have to identify one of these and make it as a reference node. Then based on this reference node, we have to write the KCL equations, Kirchhoff's current law equations. At each of these other principal nodes, that is node 1 and node 2, a voltage is assigned. So here I can assign a voltage, say V1 at node 1, and at node 2 I can assign another voltage V2, where it is understood that this is a voltage with respect to the reference node. So what is the meaning of V1? Meaning of V1 is that with respect to node 3, the potential of node 1 is equal to V1. That is the meaning of this when I write V1 here. Similarly, when I write V2 here, it means that with reference to the node 3, the potential of node 2 is V2. Okay. The last step, these voltages are unknowns when determined by a suitable method result in the network solution. So when we solve the networks using the node voltage method, these voltages are going to be the unknown parameters, and we solve for V1 and V2. So once we get V1 and V2, then we can use it to find what is the current branch, currents, etc. etc. So the algorithm could be demonstrated by means of an example. Okay, so here, just like we have written the determinant for the mesh current, I have shown how we can write the matrix for the node voltage method. Okay, so okay, so how to write the Kirchhoff's? Yeah, this doesn't change. How to write the KCL for these nodes? Can you say? I'll write the general equation KCL for this. So we can assume that some current is leaving this node. So with respect to node 1, let us discuss first. So for node 1, I have to write the Kirchhoff's current law. So I can assume currents that are leaving this node. So let me call this as I1, this is equal to I2, and this is equal to I3. So for I1, we know that KCL says that sigma I is equal to 0, or I1 plus I2 plus I3 is equal to 0, right? Yes. minus of I1, minus of I2, minus of I3 is equal to 0, or I can write this as I1 plus I2 plus I3 is equal to 0. So I1, how can I write? Or minus I1, how can I write? Which is nothing but V1 minus VA divided by the resistance RA coming in between that. So VA is, okay. VA is this voltage and V1 is this. So what is the current that is leaving this node? Current that is leaving this node is higher potential minus the lower potential divided by the resistance coming in between these two voltage sources. So that is how I wrote V1 minus VA divided by RA. That plus, that is the current that is leaving node 2. So this is the current. I2 is going to leave the node 1. So that is equal to V1 divided by RB plus the third current that is leaving node 1 is I3 current. So what is that current? I is equal to V by R. This is the equation I'm using. Okay. Current is the ratio of voltage to resistance. So what is I3? The voltage that is coming across this resistor divided by the value of this resistor. The voltage that is coming across this is V12 or V1 minus V2, right? So that is equal to V1 minus V2 divided by RC. This is equal to 0. So that is first equation. Similarly, we can write one equation for node 2 as well. Assume that currents are leaving like this. With a reference to node 2, I can write V2 minus V1 divided by RC. So let me use a different color so that you can follow easily. So one is the current that is flowing leftwards. And one current is going downwards and one current is going rightward. So this current that is going towards the left is V2 minus V1. So this potential minus this potential divided by the resistance coming in between. So that is V2 minus V1 divided by RC plus the current that is flowing down is nothing but V2 divided by RD plus the current that is going right side is V2 minus the voltage here is VB, okay, as polarity is marked, minus VP upon RA. So that will be equal to 0. That is the second equation. So these are called the node voltage equations that we have written for this circuit. Okay. So did you follow?
Yes, sir.
Okay. I hope that you are too saturated. From your sound itself, I can understand that you are very tired. So let us conclude today's lecture here. Okay, shall we conclude for now? So we'll
Yes,
have
sir.
another lecture.
Yes, sir.
So most probably, okay, you watch whether I am scheduling any class tomorrow morning. If I do not schedule any class tomorrow morning 5:30, then we'll have class day after tomorrow. That is Monday morning. Okay, 5:30. Okay. How do you find the classes? Are you able to follow?
Yes, sir.
Okay. Is the speed good or speed too slow, or what is your feedback on this? Are you comfortable with this? So in chat message, you can save time. Okay. Matrix method. I hope that's answer for matrix method. Matrix method cannot save time, but we can use it for writing programs in computer. Okay. Anyway, we'll conclude this lecture. So you watch carefully. Most probably, if I am not scheduling any class tomorrow morning, then we'll have class tomorrow, day after tomorrow morning. That is Monday morning. Okay, 5:30. So you check the great learning whether any class is scheduled or not. Okay. So we'll continue from here, and we'll see the network theorems. Hopefully, we can start with network theorems. Then after that, we'll do some demonstration of these theorems that we study using the virtual labs. So that will cover your lab part also. Also, it will help you in understanding the subject better. Then we'll shift to move to the last unit, that is the two-port networks, where we will write the network uh, parameters, how we can write the hybrid parameters, ABCD parameters, etc. Then we'll come back to the network analysis in the, that is sinusoidal transient and steady state analysis, where we'll introduce the Laplace transform and try to solve the network problems. So I don't know whether time will be available to reach up to there before the midterm. So whatever topics we cover up to this midterm, because midterm timetable is been published. So during that time, whatever portions we complete, we will have an exam for that. Then we will conduct some extra classes after the midterm too, like extra class to cover the remaining portions that will be left out. So most probably, I think the Laplace transform will be left out, because Laplace transform is very important for network analysis. You can solve much of the problems very easily. Then some topics like magnetically coupled circuits and all, I have left in the unit 1. So that also we have to cover. Then what is remaining is that theory, that is the network theory, trees, networks, branch. That is a theory part. You can read and understand also. Less numericals are coming, but for if you're preparing for gate exam, then you can expect questions from that tree, branches, etc. So that most probably I will push towards the end. If people are genuinely interested, then only I will cover that. If you have any doubts, then we can have like an interaction session, like doubt clearing session, because that is mostly theory part. If you can read and understand, it is network core theory only. The concepts are will be covered like this. That is Norton's theorem, Thevenin's theorem, how to apply the KCL, KVL, then the Laplace transform, how to determine the initial condition, then the transient parameters, etc. We will cover, because they are very important. They are core to the network analysis, without which the subject will not be complete. Okay, so we'll meet tomorrow or day after tomorrow. Okay, we'll end this session now.
Thank you, sir.
Thank you, sir.